everyone, welcome. Today we are going to take a very important question, that is question number 1C of paper 2, that is asking us to evaluate 0 to infinity tan inverse Ax by x into 1 plus x squared dx, and there are constraints on A. A is greater than 0 and A is not equal to 1. This was asked for 10 marker in paper 2 in 2019. Now this question, before I start solving it, is important that why it was missed out. This question, when you see it, what it appears to your mind. First thing we must know that why this question is in paper 2. If I say paper 1 calculus and paper 2 real analysis and complex analysis, this is also a contour integration. Alright, so this can come over here. And in calculus it is explicitly mentioned infinite integral and improper integral. Here it is only mentioned improper integral. So the point I am trying to make, that this question can be done by two methods. And this concept is very simple. If I talk about calculus, we have already studied about method of differentiation under the sign of integration. So we have to first analyze, because in paper they can ask you explicitly to do by contour integration or by using method of, there are two approaches. One approach is method of differentiation under sign of integration, and another is a contour integration. Questions can be interchanged in paper 1 and paper 2 as regards calculus and real analysis. So I have taken this question because maybe next year the same question they may give you the particular method that you have to do by contour integration. So I found it pertinent to make a clear understanding between both the methods. Alright, now I would like to give you some perspective that whether UPSC has asked such kind of questions or not. Yes, they have indeed. I am going to take one question, that is 0 to infinity tan inverse alpha x tan inverse beta x divided by x squared dx. We have to prove this is equal to half pi by 2 log of alpha plus beta to the power alpha plus beta divided by alpha to the power alpha beta to the power beta. Alright, and they have asked one more question in 1991, that is 0 to infinity log 1 plus b square x square divided by 1 plus b square x square dx. Here it is a square. So first thing first is that the moment we see such kind of question, we must have a clear understanding as to from which area it is coming. So I can speak about it when it is in calculus. So basically this question should have appeared in paper 1, but that has not appeared so. And why I am also going to give prime importance to this question, because real analysis is already asked for more than 80 marks if you include this, and complex variable only for 45 marks. So if you give this 10 marks to contour integration, so that will be 55 marks. So just to avoid confusion, I am going to solve this question through both those methods. Alright, so I will first approach this method by complex variable, because I deemed it fit that it should be done in the right earnest. Alright, so this is a contour integral, and we can write this as 0 to infinity log of 1 minus I.A.S divided by x plus 1 plus x square. Since I am talking in terms of z, I will replace it with z. That's not a problem. Now, why I have changed this, I will first give you a brief understanding. we know the logarithmic of any function is log under root x square plus I ln x square plus y square underscore plus underscore plus I tan inverse y by x. So here we can see over here that I can write this thing in terms of what is going to be the imaginary part of this one. Imaginary part is going to be minus of I tan inverse z by a. So that is a minus. I have not taken minus. I will take it after I have solved this equation. All right. So first thing is that we are going to, why I have changed, because in contour integrations we have to take, so this is the tan inverse ax can be the imaginary part minus of this one, and I can approach further. So here where C is the contour consisting of large semicircle, we are taking a notation where all the poles of integrand lies in the upper half plane and part of real axis from minus r to r. So this is the diagram that it goes from minus r to r, and this is a semicircle. An integrand is lying in the upper half of the plane. Now we are going to use the Cauchy's residue theorem. So we can use this as f z p z by Cauchy residue theorem. Minus r to r log of 1 minus I.A.S divided by x into 1 plus x square dx plus integral on this contour log 1 minus I.A.S, taking the z over here. So you can see over here that limit z tends to infinity for 1 by z square plus 1, this gives us 0. So we can say that limit r tends to infinity f of z dz is equal to 0 over this contour by Jordan's lemma. So this one is nullified. All we have to find out is this one. So what it will give us? It is going to give us minus r to r log of, and this is whole equal to 2 pi I summation of r plus. So we are getting it 1 minus I.A.S divided by x into 1 plus x square dx is equal to 2 pi r, and these are the summation of residues. So find this one, and our values of r tends to infinity to minus infinity. So I am going to change it because r was tending to infinity. So I have replaced it like this. Now I am just concerned with this part, and I will just find the residues at the poles, and then I will find the value. So if we start with this one, this gives me minus infinity to infinity, log of 1 minus I.A. x divided by x into 1 plus x square dx. Okay, and this is equal to 2 pi I. I'm going to find out the values. First, our poles are z is equal to 0 and z is equal to I and z is equal to minus I. I can see that on upper half plane ranging from minus r to r. So here this is over here minus I and I. So minus I is outside the pole. So we are only concerned with z is equal to 0 and z is equal to I. So z is equal to minus I lies outside the contour. So we will not factor it. What about our z is equal to 0? At z is equal to 0, yes, it lies. So we will find the residue. The residue is at z is equal to 0 is limit z tends to 0, and this is what? Log of 1 minus I A z by z into 1 plus z square, and here that is z into fz. So z will be cancelled and this is 0, so log 1 is 0. So we have got at residue 0. So only we have to find residue at z is equal to I. So at z is equal to I, the residue is at z is equal to I is limit z tends to I, here z minus I into log of 1 minus I Az divided by z into z minus I into z plus I. I have just factored this z square plus 1. So this is cancelled. We will put the value of z. So this become what? This become log of 1 I become I square. So this become minus and minus become plus. So and here what is 2 I into 2I, I into 2I. What is this? I square becomes minus. So this becomes our minus of 2. So we have found out the residue. So first, now we can write this as how much? 2 pi I into, only we are concerned with this part. So this will give me log 1 plus A divided by minus 2. So 2 will get cancelled. So we have got the values. So this has given me how much? This is minus of pi I log 1 plus A. Okay. So here we can see that this is minus pi I. Now I will write this as minus infinity to infinity. So I can write it 0 to infinity also, because that will be the 2 times of this one, x 1 plus x square dx, and this becomes here 2. So this 2 will go in the denominator. Alright. Now we have found very close to our answer. What is log 1 minus ax? That is minus, that is the imaginary part of tan inverse minus tan inverse z. So if I am going to write it, so I have to write the imaginary part. So I am equating the imaginary part now. Equating imaginary part. So when I am equating imaginary part, that is the minus of tan inverse, here it is a z, because not factored. So this become a x over here divided by x plus x into 1 plus x square. This gives me how much? Minus of log 1 plus a divided by 2. So minus sign and minus sign will get cancelled. So we have got our answer as 5 by 2 log of 1 plus a. So this is how we are going to solve by contour integration. And suppose this question, if you are using the method called differentiation under the sign of integration, this is sometimes also taught at class 12th level also, the same concept for integrals whose for such integrals which is difficult to evaluate. So if I use it by differentiation under sign of integration, there are certain questions like this. Certain questions, only 5 to 6 questions, you can check it out in the textbooks. So if I write this, I is equal to 0 to infinity tan inverse of ax divided by x plus x into 1 plus x square dx. Now we have understood the theory of this, so we have to differentiate with respect to parameter a. So if I differentiate it, what it becomes? It becomes 0 to infinity, alright, and this becomes 1 plus a square x square into 1 plus x square, and differentiation of ax with respect to a is x. So here we can see xx is getting cancelled. Alright, now this is if you apply some approach of multiple integral which we have studied. So if I am going to use double integration, say di by dA, and it runs from 0 to a, and this runs from 0 to infinity. This is simply a simple manipulation, nothing else. Now if I change the order, this becomes 0 to infinity, and I integrate this respect to a, what it will come? It will come tan inverse of ax 1 plus x square is kept constant, and integration for this part, the 1 by x. So what we are seeing over here, that we are getting our integral which where we started with. So this is equal to I. Here you can see a is greater than 0. If it was greater than equal to 0, we could have found the arbitrary constant by just putting a is equal to 0 in this becomes 0. So that could also be done. But here we have to be very vigilant because they have not given equal to 0. So we have to do a simple manipulation and we will get this solution to this answer. So what I am getting? I am getting one important result, that is I is equal to integral 0 to a di by dA, and I have to integrate this one also with respect to a. So now we have got certain values. I am again going to use an important thing that which I have done previously, that is 0 to infinity 1 by 1 plus a square x square into 1 plus x square dx. So this can be used by partial fraction, 1 by 1 minus a square, 1 by 1 plus x square minus of a square divided by 1 plus a square x square dx. And now I am going to integrate this one. So what is the integration of this one? This is tan inverse x minus of a square tan inverse of a x of this part also a. So this becomes 0 to infinity. So here we have to be vigilant. A is greater than 0, not a is not equal to less than equal to 0. So here that's why we have to take the plus sign. So this becomes how much? Pi by 2. This become a, again this become pi by 2. We can take pi by 2 outside, and 1 minus a divided by 1 minus a whole square. So what I get? I get my di by dA is equal to how much? Pi by 2 log pi by 2. This is how much? 1 plus a itself. So I will just plug this value in this integral. It is I is equal to pi by 2 integral 0 to a 1 by 1 plus a dA. So this is my pi by 2, and integral of this one is log 1 plus a, limit runs to 0 to a. So this will be again pi by 2 log 1 plus a. So what is the moral of the story? That no matter which method you will take up, if you know your understanding and concept, answers are going to come the same. That is pi by 2 log 1 plus a. Even in complex variable got this answer. So the point I am trying to make it very simple. We have to be very much careful about the methods that we take, concept that we have learned, and if we apply it with simplicity, without making any mistake, the answer will be same. So thank you for watching. Please like, share and subscribe.